Hey everyone. So for my Capstone project, I decided to work with the exoplanet data available on NASA's website. Um, it's a lot of it's listed here. Um, if you're curious, I have the links to the data and exhaustive explanation of the columns on the Jupyter notebook itself. But essentially, it's a data set consisting of all the confirmed exoplanets or planets outside of our own solar system um, that have been confirmed through various sources. Here we can see the columns that are present in the data set. I'm not going to go through all of them. You can do so yourself if you feel intrigued, but they are on the notebook as well. Full disclosure, initially what I attempted to do was find a relationship between the host star metallicity, which is a description of or a measure of all the heavy elements present in the star that the exoplanet is orbiting, and other features within the dataset. But that was unsuccessful, so I shifted over to trying to learn the planet's equilibrium temperature as the dependent variable, and using some combination of the other columns as the feature set. So that's the approach that I'm taking. That's the question I'm essentially trying to answer. Here I'm just importing many of the packages that I'm going to need throughout the data exploration and feature extraction and learning process itself. I read in the CSV file, which I downloaded from the website, the link being above, and just take a quick look at what the data was kind of looking like, what you can see here. Here are just the columns printed out. So one of the first things I decided to do in my data exploration, and I guess kind of feature extraction, is remove any columns that don't add any value. Many of these columns, if you go back up, are things like links to papers that support the claims or measurements that are listed here in these columns. Obviously, we're not going to be using these links to do any type of learning, so I removed columns of that nature. The next thing I did was take a look at some general statistics in the data set, right? So what the mean of some of these values are, for instance, what type of spread within the values through the standard deviation we're seeing. For instance, here, the equilibrium temperature, which is the dependent variable that we're trying to learn, we can see that it has a mean of about 1091. I believe these units are in Kelvin, I would imagine, the standard scientific unit for temperature, with a decent spread of values, right? So from there, I'm just listing out the statistics in a more readable fashion, so that if I were to, for instance, print this notebook in PDF form, a reader of the PDF would not be overwhelmed by one huge column, but separate columns. So that's relatively insignificant. All right. Something I wanted to, I guess, something that I thought might be interesting is seeing which one of these features has the largest spread. So I sorted by standard deviation, right? And it appears that this orbital period is the one with the largest spread. Just thought it was interesting. Wasn't sure what type of information I'd retrieve from looking at the spread, but just felt like doing that at the moment. The next thing that I looked at was the covariance matrix for this feature set, and also the correlation matrix, which is probably a bit more important for this feature set, right? So as I stated previously, I decided to use the equilibrium temperature as my dependent variable, which I will learn. So I decided to look at which other features have the highest correlation and covariance with respect to the equilibrium temperature. And as you can see here, the radius of the planet itself is most strongly correlated to its equilibrium temperature. After that, it's its mass, then the luminosity of the star, then the effective temperature of the star, and so on. So from exploration of this data here, I was able to choose which features I felt were going to be the most important and most useful when attempting to learn for this dependent variable. So what I did was I created a scatter plot of the top 6 features that most strongly correlated with the equilibrium temperature. So here you can see the equilibrium temperature on the y-axis and the other features on the x. And I mean, just looking at the scatter plots, it does look like there is some dependence there. It doesn't look completely random. All right, so we're going to move on to ETL. And as I mentioned above, from the data exploration, I decided on these, 5 features or 6 features, right? Which actually turned out to be 5, I believe, because I dropped this insole feature because there's just too many of them were not numbers in the data set, and keeping it would reduce the total number of data from which I can learn from too drastically. So I dropped that particular column and ended up with 5 features that I was going to work with. So from there, I also remove at some point any entries that contain NaNs. I did it in one line here. Yeah. So what ended up happening is the number of data entries that I will be working with was reduced to 947. And then it's further reduced here because I decided to remove any outliers through use of this function, which essentially finds any entries whose value is greater than 3 times the standard deviation for that particular feature. So those entries were also removed just to avoid outliers too strongly influencing the learning process. And this is kind of what I ended up with here. So a quick little view. I decided to save that off just in case I wanted to pick up from here. I'd have to repeat every step that I've completed so far. So from there, my first approach was to work with PySpark. Not for any particularly good reason, just because it's the first thing that came to mind. As you can see here, I'm loading in the Parquet that I saved off previously into this PySpark data frame. Here I define some helper functions that allow me to further process the data. One that creates a vector, when it turns a column of just regular values into vector values, um, another function that scales the values to be between 0 and 1, and so on and so on. So I make use of those functions and make sure that all the features that I'm using to learn have been scaled appropriately so that their particular units don't affect the learning process, and all the features are on a level playing field to begin with. And this is just illustrating what the features and their ranges were looking like prior to scaling and being turned into vectors, and then after scaling and being turned into vectors. So you can see none of these values for the features are greater than 1. I save that off to continue the process. Alright, so I read in the pickle that I had saved off previously, and create the new data frame that creates a vector from the input columns to create my feature sets. And you can see the result here. Alright, so now there are 2 columns, one being the combination of features and the other one being the dependent variable. Alright, I split this data into a training and test set, and essentially just feed it into the linear regression library provided by PySpark. And essentially these are the results here. These are the coefficients for my feature set, which I further illustrate here, essentially stating that my dependent variable, is a function of this times the planet radius, this times the star mass, this times the star luminosity, and so on and so on. And interestingly enough, we can see that the largest coefficient is in fact for the planet radius, which, if we go back to our data exploration section, we do see that the planet radius has the strongest correlation, so that makes sense. Okay. Next, I evaluate my model, right? I use standard metrics such as root mean squared error and the R2 here, and the model performs okay, I would say. This R2 value isn't spectacular. The closer it is to 1, the better. But this root mean squared error is less than the standard deviation at the very least, and is less than the mean of the data or the dependent variable. So that's comforting. Just for fun, I also repeated the process using the scikit-learn library. But before we go on there, as you can see here, I did evaluate the model on the test data as well on my test set, and got a similar R squared value and root mean squared. So that at the very least would tell me that I am not overfitting my data, right? And there is that the fit is not overbiased. So as I was just saying, I decided to give scikit-learn a go, and here I'm just rereading in the part K I saved off earlier, defining my features and my dependent variable, scaling the features so that for the same reasons that I stated previously, and splitting my data into a test and train set. Here I'm just instantiating an instance of the linear regression class and training my model on it. Pretty straightforward. And here are the coefficients, which aren't too different from the coefficients that PySpark identified. We get a similar root mean squared error here and a similar R squared. So nothing too crazy. So to I guess finish it off, as per the requirement for this capstone, we also needed to try a neural network, a deep learning neural network approach as well. So I decided to do it using Keras and defining a 3-layered neural network. The first layer being 12 neurons, the second 8, and the last one having to be 1 because this is supposed to approximate multiple linear regression, right? I decided to use mean squared error as my I guess measure of performance, to train the model on. And from there, I just passed in the training set with about 300 epochs. So this number I actually played around with a bit. I'm going to jump down to the bottom here. As you can see, after about 100 epochs, we can be pretty confident that our model has converged. So 300 is more than enough. And after training, we can look at some of the validation metrics, and we see that the root mean squared error is about the same as we've seen previously. Nothing too crazy, and so is R squared. So all these models perform relatively equally, and that is essentially the end of my presentation. Thank you.